This video will cover 3 past paper questions as worked examples on the topics of work, energy and power. So in this first question we're going to look at, we've got this block being pulled up a slope by a tension of 91.5 newtons. There's also a frictional force acting on the block, which isn't labelled on our force diagram. So we've got some frictional force opposing it here. And we're told that the speed of the block increases from 1 meter per second to 7 meters per second over a distance of 8 meters. This is a question that we could solve using Newton's second law and Suvat equations, but we're asked to, because the forces are constant, but we're asked to solve it using an energy method. So when we're using an energy method here, there's a few ways that can be laid out, but the work energy principle that I'm always going to use is that we have the initial energy, and in that case, in this case, we're looking at kinetic energy and gravitational potential energy. So we're looking at initial energy plus the work done by any forces that aren't weight, because that's taken into account with gravitational potential energy, is going to be equal to the final energy of our block here. So if we're doing this in this situation, initial energy, we've got an initial kinetic energy, which is going to be half mv squared, and we know m is 6, and we know v is equal to 1, so just times 1 squared. And then in terms of gravitational potential energy, we don't know how high it starts, but we can choose where to draw our reference points for gravitational potential energy. So let's use our reference point for gravitational potential energy from the point of start. So there's no gravitational potential energy, and then we've got work done. Now, there's 2 things that are doing work, apart from weight, that are doing work on this block. We've got a tension of the string, so that's going to be 91.5 times by the displacement in the direction of the tension, which is 8. And then we've got the work done by friction. Now, we don't know the friction, but the displacement is in the opposite direction to friction, so this is going to be subtract 8F, because the work done by the friction is going to be negative here. So we can say add the negative F, but I'm just going to write subtract 8F. And this is going to equal to the final energy. Now here, the final energy is going to be the final kinetic energy, which is going to be half times mass times our velocity squared at the top, which is times 7 squared. And then our gravitational potential energy. Now this one takes a little bit more thinking, but we know it's moved 8 meters up the block. We know that this angle here was 30 degrees. So this is a sine 30. The new height in relation to our base reference is 8 sine 30. So here we're going to do plus m, which is 6g. So, m times g times by 8 sine 30. And at this point, we just have an equation in terms of f to solve. I'm not going to worry too much about going through and solving that. You can all solve that equation. And we end up by getting F equals 44.1 newtons. The next part of the question isn't really anything to do with work, energy and power. We're asked for the coefficient of friction between the block and the plane. I'm going to just skim over this because it's not really what we're focusing on, but you'd be able to get that the reaction force of the block is going to be equal to 6g cos 30, and then using F max equals mu r, you're just going to sub in your F, which you know is your maximum friction because it was moving. You're going to sub in your r, and you're going to solve, and you should end up with mu is equal to 0.866. You can work through that if you want, but that's not really a work energy power question, that part. Now, we're asked for the power of tension in a string. There's 2 definitions of power. Average power is equal to work done over time, and instantaneous power is the rate at which work is done. But the problem here is work is being done at a quicker and quicker rate because the block's accelerating. And instead, we're going to want to use that power is force times velocity. Now, I've written F here, but I've used F for friction, so I'm going to say our tension times velocity. And in this case, this is nice and easy now because our tension is 91.5, our velocity is 7 meters per second, and we can just multiply those together, get 640.5, and our units is watts. Okay, I want to look at a new question now, so I'm going to scroll across. In this one, we're not just travelling along a nice straight slope, so we've got this roller coaster going here. First part of the question, we're told the car's being pulled up the slope at a steady speed of v by a force of 2160, and we're told the power. Again, here we're just going to start off using the power equals force times velocity. And if we sub in here, we'll get 3780 equals 2160V. And straight away we can solve that and get our expression for V, or our result for V, which is 1.75 meters per second. The real part of this problem starts in the second part. So the pulling force is removed, and we've got this car just traveling under gravity and against resistances. So it's not actually doing any work. There's no engine that's doing work anymore. There was no pulling force. It's just free to go. But we'll use the work energy principle as before and consider each force one at a time. So for the work energy principle in this question, we're going to do the initial energy. And this is going to be initial kinetic energy and initial gravitational potential energy. So initial kinetic energy is going to be half times our mass, which we know is 380, times our velocity squared. Well, our velocity at the start is 2, so times 2 squared. We've got initial gravitational potential energy. In this case, I'm going to take the floor as our base reference because it's natural. It's where we're given the distances from. So we're going to have 380g times 20. And then we've got to think about the forces doing work. So again, we're not going to consider the work done by weight here because it's already going to be taken into account with the gravitational potential energy. But what we are going to have is the work done by the average braking force. Now, we're told the average braking force is 150. We're also told it travels 100 meters along the track. This displacement will always be in the opposing direction to the braking force. So the work done by the braking force is going to be negative 150 times 100. We've then got the work done against resistance to motion. That's what we're trying to find. But we're going to be subtracting the work done against the resistance to motion. This is where language is a little bit weird. The work done by resistance is negative. The work done against resistances is positive. So we're going to get subtract work done against resistance is equal to the final energy, which is just going to be the final kinetic energy and our final gravitational potential energy. So our final kinetic energy is just going to be half times 380 times 10 squared, and our final gravitational potential energy, so that's a plus, is 380g times by our height above the ground at that point. At this point, rearrange and you'll get that your work done is 22620 joules. Final question I want to look at is more related to power and is looking at a more difficult power problem here. So in this case, we're told we've got a car traveling along a straight road, going at a steady speed of 50 meters per second with a power of P. And then the power reduces. Naturally, the car's going to begin to decelerate if that happens. And we want to use this information by how much the power reduces and the deceleration to find P and to find F here. So I would always recommend on these questions getting a force diagram down to just show what's going on. So initially, well, what forces are acting? We've got some frictional force, which we don't know, acting on a car. And we've got some driving force. Now, we're told it's traveling at a speed of 50 meters per second. So by rearranging power equals force times velocity, and in this case our force is our driving force, we're going to get the driving force is equal to power over velocity. So in this case, P over 50. And using Newton's second law to the right, because the acceleration is 0, we're just going to get P over 50. So that's P over 50, subtract F, is equal to 0. That's our starting point. Now, we've then got a new situation. When it's still traveling at 50 meters per second, the power reduces by 20%. So the new power is going to be 0.8p. And we're still using the velocity as 50 because we're thinking it's in that instance that the car begins to decelerate and is at 0.08. So we're still doing power over velocity and we're still using that velocity as 50. And we're told the F is unchanged. But what we know now is the acceleration to the right is going to be negative 0.08. So using Newton's second law now, we're going to get 0.8p over 50. Subtract F is equal to negative 0.08 times by our mass of 1500. And voila, we've got some simultaneous equations. These two equations here, for a variety of ways you could solve them. One of the most direct ways is doing equation 1 subtract equation 2, which will make the f's disappear and will just leave you with p over 250 is equal to 120, and we can solve. And we're going to get that p is equal to 30,000, and that's 30,000 watts, but p was just the value. And then we can sub in and get f, which is going to be 600. Thank you very much.